So now we're dealing with augmented Lagrange multiplier method. So basically the idea of this method, let's illustrate it on a 1D case. So the idea is having something called penalty function, which means that when the answer is not in the feasible area, for example right here, this is the function, but we want to only be smaller than 0. So we will define this penalty function like this, like e to the power of x minus 1. So when the value is positive, then you will receive a positive penalty. So the more you deviate from the feasible area, for example, if you're here, then you get relatively big penalty function, penalty, and if you're smaller, you get smaller penalty. So what we define something called phi p, which is defined right here. So in this case, the more the p is, if p goes to, for example, if it goes to infinity, we'll reach something called the ideal penalty function. So in this case, you have the function looks like this. So when it's smaller than 0, the penalty is 0, but if you go slightly more outside of the feasible area, the penalty will be infinity, which you will not take. But in this problem, when p gets very big, you have numerical problems. So in order to solve that problem, we'll define something called phi p mu, which controls actually the gradient around, like the derivative around 0.0. So it's always mu x. So like the derivative here is always mu, which is very good in this case. So you can control the slope, let's say, not to be too steep, and then we can define our function like this, like what we said, is like the regular function plus the penalty function. So we'll have an update every time after one iteration. First of all, you get optimal function, optimal place of such this function. So it's with the penalty. For example, you get the first time is here. So how are you going to update the next penalty function? So what we will do is we'll take this point and we'll get the slope. So this will be the slope for the next mu. So for this second step, the second iteration, the slope right here will be the slope that we find over here. It will be the same slope. So in this case, the penalty function will get bigger, and then your answer will be closer to the actual minimum inside the feasible area.